Welcome to the 10th session on electrolytic conductance, and this is the last session on electrolytic conductance. And in this session, we will be dealing with ionic strength and Debye-Huckel limiting law. Ionic strength has been introduced to measure the concentration of the ions in solution, especially when you are having more than one electrolyte added to the same solution. It was defined by Lewis and Randall in the year 1921 and is based on dissociation of salts, acids and bases in aqueous solutions. Ionic strength was introduced to represent the deviation from activity coefficients with concentrations. As you all know, activity coefficient, which is denoted as gamma plus or minus usually, and this activity coefficient deviates from normal value unity. The normal value, that is in the ideal conditions, it should be unity. So, the deviation from this value is mainly due to interionic attractions existing between the ions in an electrolyte, and the value increases as the concentration decreases, and it reaches up to unity, or you can say that is equal to 1, and all other conditions, that is when we increase the concentration, when we are going to increase the concentration, the value decreases and you can see they will be all fractions. So, under ideal conditions you get the value as unity, or in that cases we can neglect the activity coefficient and activity will be directly equal to molality, or you can say the concentration of the electrolyte. So, here attempt has been made introducing the term ionic strength and Debye-Huckel limiting law in order to explain the deviations from ideal conditions in concentrated solutions. So, first we will see what is ionic strength. Ionic strength is defined as half the sum of the terms obtained by the product of molality of each ion and square of its valency. That is, you have to take the product of molality with square of valency of each ion. So, this is the expression. If you are having a number of constituents, that is the electrolyte consists of many electrolytes, it is a mixture of electrolytes, you have the constituents being 1, 2, 3, etc. So, we will consider the molalities being M1 for the constituent 1, M2 for the constituent 3, M3 for the constituent 3 and so on. And similarly, Z1, Z2 and Z3 are the valencies of different ionic species. You can represent ionic strength, which is denoted by the letter mu, is equal to half into, because it is half the sum. Okay. So, half into M1 stands for molality and Z1 for its valency, and valency should be square. So, Z1 square, then M2 Z2 square. Here it is M1 Z1 square, M2 Z2 square, M3 Z3 square and so on. And this will give you the ionic strength of that particular electrolyte. Now, if you are having an electrolyte where we have only one cation and one anion, in that case ionic strength will be equal to, that is you are having only a cation and an anion. So, M plus represents the molality of cation and Z plus that the valency of the cation, and M minus and Z minus that of the anions. Okay. So, mu is equal to 1 by 2 into M plus Z plus square plus m minus Z minus square. So, you are having only two factors to be added up, that is one of the cation and the other of the anion. Okay. Now, we will go for the problems based on this. So, the first one is a very simple one. You have to calculate the ionic strength of 0.1 molar NaCl solution. Now, before going to the calculation of an ionic strength, what we have got is only the molality of sodium chloride. This is the molality of sodium chloride. We do not know what are the molalities of sodium ions and chloride ions. So, first we will see how sodium chloride dissociates. It dissociates as Na plus Cl minus. Here you can see, if I take 1 mole of sodium chloride, you will get 1 mole of sodium ions from that and 1 mole of chloride ions. Okay. So, in this case, the concentration of sodium chloride taken is 0.1 molar. In that case, you can see from the above expression, that is, the molality of sodium ions will be equal to molality of sodium chloride, and similarly chloride ions also the molality will be equal to the molality of sodium chloride. And so, if the sodium chloride, if the concentration is 0.1 molar, and that will be furnishing, it will be completely ionized, and therefore, that will be 0.1 molar sodium ions and 0.1 molar chloride ions. Now, let us see what are its valencies. So, here we have been expressing the molality, and valencies in the case of sodium, it is unit positive charge. So, valency is 1, and that of chlorine valency is again 1. Now, we can calculate the ionic strength. Ionic strength will be equal to half into molality of Na plus into valency of Na plus square plus, do not forget that, molality of Cl minus into valency of Cl minus square. Now, we can substitute the values. Half into molality of sodium chloride is 0.1, valency is 1, therefore, there is 1 square plus molality of chloride ion, again that is again 0.1 into 1 square, and when we add up, the answer will be 0.1. Okay. Now, let us go for the case when we are having a different electrolyte, that is calcium chloride. Calculate the ionic strength of 0.2 molar calcium chloride solution. So, as a first step, as I have told you, first write how the electrolyte gets ionized. That is, you will have Ca2 plus 2 chloride ions, because here you can see that there are 2 chlorine attached to calcium atom, and therefore, that is 2 Cl minus. Now, here one more point, if I take 1 mole of calcium chloride, you will get 1 mole of calcium ions, that is for sure. So, what is the concentration of calcium chloride? The same will be the concentration for calcium ions. But when we come to the chloride ions, it is slightly different. See, from 1 mole of calcium chloride, it gives 2 chloride ions. 2 chloride ions means, if I start with 1 mole of calcium chloride solution, it will be furnishing 2 into 1, that is equal to 2 moles. That is twice the concentration of calcium chloride solution, you will be getting chloride ions. So, here we have to apply the same condition, that is, first we are going to write the molality, that is, I am starting with 0.2 molar calcium chloride. So, calcium will be the same as the concentration of calcium chloride. So, I can put it as again 0.2 molal, while in the case of chloride ions it is twice the concentration of calcium chloride. So, that is 2 into 0.2 molar. Now, we will write the valencies. Calcium, the valency is 2 because it has got 2 plus, that means its valency is 2. Chloride, unit negative charge, therefore, its valency is 1. Next, what we can do is we can go for the ionic strength. Ionic strength mu is equal to half into molality of calcium ions into valency of calcium ions square plus molality of chloride ions into valency of chloride ions square. Okay. So, we can substitute that. Mu is equal to half into molality of calcium is 0.1, no 0.2 into valency of calcium, that is 2 square, plus molality of chloride ions is 2 into 0.2 into valency 1 square. Now, when we calculate, we will get the answer as 0.6. So, here please note, whenever you get an electrolyte, you better write down its ionization and find out the molality. Otherwise, you may go wrong in calculation. Now, here comes another example, which is actually the main application of ionic strength, because ionic strength is very much needed when we have a mixture of electrolytes in a solution. Here, this is a problem like that. Calculate the ionic strength of a solution containing 0.1 molar KCl solution and 0.2 molar potassium sulfate solution. So, you are having 2 electrolytes together in a electrolytic solution. Here, we have to write down the ionization of both the electrolytes. For example, I am taking KCl. KCl will ionize as K plus Cl minus. Okay. When we go for potassium sulfate, it is slightly different. You have 2 potassium ions plus SO4 2 minus. Here again, I am going to start KCl with 0.1 molar solution, which will be completely ionized, and it will be giving 0.1 molar potassium ions and 0.1 molar chloride ions. So, these are the molalities. Okay. Followed by, we will be writing down the valencies. Valency of potassium ion, unit positive charge, therefore, valency 1, and that of chlorine is also 1. Now, let us come for the potassium sulfate. Let us see what will be the molalities. We are starting with 0.2 molar potassium sulfate. When it is completely ionized, you will get 2 K plus ions, that is twice the concentration of potassium sulfate. So, here it will be 2 into 0.2 molar for potassium ions, and for sulfate ions it is only 0.2, because you are getting only 1 ion from that, 0.2 molar. Okay. So, we have got the molalities. Next, I am going to write the valencies. Potassium, it is unipositive, therefore, that is 1, and sulfate, the valency is 2. Now, here comes the point to be noted. Now, both these electrolytes are present in a solution together. So, the solution as a whole will have potassium ions both from KCl as well as from potassium sulphate. So, you have to add up both the ions, the molalities should be taken together, and that will be the sum of K plus ions, molality of K plus ions from KCl as well as molality of K plus ions we are getting from potassium sulphate. So, here we will have to calculate the molality of K plus first. K plus will be equal to molality of K plus from KCl, that is equal to 0.1 plus molality of K plus ion from potassium sulphate. Here we will have 2 into 0.2, that will be the molality of KCl. The others it is okay because all are single ions. So, molality of Cl minus will be 0.1 itself, and that of sulphate same as that in that electrolyte, 0.2 molar. Okay. So, this is the application if we take ionic strengths rather than any other notations. So, here we are going to find out the ionic strength of this electrolyte, because you are having two electrolytes, that will be half into molality of K plus into valency square of K plus molality of chloride ions into valency of chloride ions square plus molality of sulphate ions into valency of sulphate ions square. Okay. Now, let us substitute, that is half into molality of K plus ions will be 0.1 plus 2 into 0.2, that will be coming around 2 to the 4, that will be around 0.5 into, I will put this in a small bracket, into valency of potassium ion square, that is 1 square, plus molality of chloride ions, that is 0.1 into, again its valency is 1. So, into 1 square plus molality of sulphate ions, that is 0.2 into valency square, 2 square, and you will get the answer as 0.70. So, this is one of the applications when we take ionic strength. Next is Debye-Huckel limiting law. Debye-Huckel limiting law, the word limiting law stands for, we have to consider the concentrations in the limiting value, that is in very dilute solutions. We know that it relates between mean ionic activity coefficient of an electrolyte to valency of its ions and ionic strength. So, it is a equation relating all these things. Now, it is always applicable to the limit of infinite dilution. Again, for stronger solutions it shows deviation. Now, the expression mathematically it is written as log gamma plus minus, this stands for mean ionic activity coefficient. Okay. So, that is equal to minus A. A is a constant which depends upon the nature of the solvent as well as the temperature. So, it is a constant which depends upon nature of the solvent as well as temperature, and Z1 and Z2 are the valencies of cations and anions. So, cation and anion valencies are denoted as Z plus and Z minus, and root mu, mu stands for ionic strength of the solution, which we will be determining the way I have just explained. Okay. Now, when we watch this equation, you can see a negative sign applied here, because that is true. When we take logarithm of any number less than 1, that means that should be, if it is less than 1, number is number which is less than 1. Logarithm term should be negative. So, to prove that, it is written as log of gamma plus minus, that is mean ionic activity coefficient, will be less than 1 in most of the cases, and that will be equal to 1, that is a condition when it is ideal. So, this expression can be used for explaining the deviations from the ideal condition of any electrolyte, but there is one again condition, it is applicable at lower concentrations only. So, it is very important, do not forget the negative sign. So, that is mentioned here, that is negative value of log mean ionic activity coefficient always is less than unity, and this is true in almost all dilute solutions, but there is again deviation when the concentration increases. Now, let us speak about the constant A. I told you constant A is a constant which depends upon nature of the solvent as well as temperature. So, usually we dissolve electrolytes in water, or you can say we deal with aqueous solutions. When I am dealing with aqueous solution, and if I maintain the temperature to be 298 Kelvin or it is 25 degree Celsius, the value is again constant because solvent is fixed, temperature is fixed, and therefore, the value is taken as 0.509. So, that is a constant. So, I am applying that to the equation, log of mean ionic activity coefficient is equal to minus 0.509 into Z plus into Z minus to root of mu. Now, this expression can be considered as an expression for a straight line where the y-intercept is equal to 0. That is, the expression for straight line is y is equal to mx plus c, where c is the y-intercept which is equal to 0. So, you do not have c in this equation. Now, m is the slope and x and y are their coordinates. So, y means log gamma plus or minus, that is y, and x will be the x axis, mu root of mu. Okay. So, if I plot this, this will be the slope. Okay. Now, if this is a slope, now how far will it be? Now, since c is equal to 0, the graph should be in such a way that it passes through the origin. The graph should pass through origin because it does not have a y-intercept. Now, what will be the condition of the slope? We know the Z plus and Z minus, they are the valencies of cation and anion. Suppose I am having a 1,1 electrolyte, both cation and anion are having valency 1. In that case, Z plus and Z minus will be 1, 1 into 1 again it will be 1 itself, and therefore, in that case slope will be 0.509. I repeat, if the valencies of cation and anion are 1, 1 into 1 will be 1 and slope of that straight line will be 0.509. If I am having an electrolyte, it can be either 1, 2 or 2, 1, it does not matter because either this will be 1 and this will be 2, or in the other case this will be 2 and this will be 1. Again the product will give you the answer 2. The slope will be 2 into 0.509, and for 1, 3 or 3, 1 that will be 3 into, it is clear. Okay. So, let us see how the graph appears. Here they have made a difference. they have taken it as negative log of mean ionic activity coefficient. So, this is on the negative side, so that it becomes positive, and here is the origin, and from origin you can see all these are passing from origin, but you can see the theoretical values as dotted lines, while bold lines are the experimental values. And here again you see that as we move along to stronger concentrations, there is wide deviation from the values, or the Debye-Huckel limiting law is applicable as it is mentioned in the limiting word. It is applicable only to those solutions which are dilute. So, that is the validity of Debye-Huckel limiting law. Now, with that we can conclude. In the session, we have been dealing with ionic strength. Ionic strength is mainly used when we have other electrolytes, or you are taking a mixture of electrolyte in an electrolytic solution, and it is given by the expression mu is equal to half into the product of molality into valence square of each ion. You have to take molality and valency square, sum it up and take the half of it. That gives you the ionic strength of an electrolyte. Next, we have been dealing with Debye-Huckel limiting law and also its validity, that is log of mean ionic activity coefficient is equal to minus A into Z plus into Z minus into square root of mu, where A stands for a constant which depends upon nature of the solvent and temperature, Z plus and Z minus are the valencies of cation and anion, and mu is the ionic strength of the electrolyte. Thank you.